All right, so now we're going to look at trig identities in greater detail and spend a little time really developing the concept of using identities in trigonometry, and then later, or in preparation for later, using them in calculus to a pretty great extent. So the good news is you already know many trig identities, though you may not be calling them identities at this stage. They look like this: sine of theta is equal to 1 over cosecant of theta. So sine and cosecant have a reciprocal or inverse relationship to each other, so long as on both sides of the equation theta is defined, or the function of theta is defined, then we know that we have an identity because they're equal to each other. And that's what an identity is. It's an equation where the left-hand side and the right-hand side are equal to each other. So another reciprocal or inverse identity would be the cosine of theta is equal to 1 over secant theta. And of course, tan theta is equal to 1 over cotan theta. And then we have the reflection, or the inverse of each of these, right? The also true statements that the cosecant of theta is equal to 1 over sine theta. I think I spelled cosecant wrong. And that the secant of theta is equal to 1 over cos theta. And cotan of theta is equal to 1 over tan theta. So there you go. 6 of the identities out of the way, already learned and mastered because you've been working with them all along. And these are called reciprocal identities. I tend to call them inverse identities. Same thing, different word. You also have 2 other identities that you're used to working with already. You know that the tangent of theta is equal to sine theta over cosine theta, and the cotan of theta is equal to the cosine theta over sine theta. And these are called the quotient identities for obvious reasons. And I tend to call them quotient identities. So we've used these in the past, but I will do a couple of examples here in exactly this way. Suppose I know that the secant of x equals 5/3, and I'm asked to find the cosine of x. Well, we know that the cosine of x is 1 over secant x, but secant x is 5/3. So this means that the cosine of x equals 3/5. This would be a reciprocal, the use of a reciprocal identity. Another example, suppose I know that the cosecant of beta is 25/7, and I also know that the secant of beta is 25/24. I'm asked to find tangent of beta. So I can use a little bit of logic, knowing that the cosecant of beta, or that, the tangent of beta, let's work from this direction. I was going to go another way. I changed my mind. That the tangent of beta is sine beta over cosine beta. But cosecant is the inverse of sine beta. So sine beta equals 1 over cosecant beta, and cosine is 1 over secant beta. So now I'm going to put in values. So I have 1 over 25/7 and 1 over 25/24, just substituting the value for cosecant and the value for secant. And then I can write this, well, the reciprocal in the numerator would be 7 on top, 25 on the bottom of the fraction, and 24 on top, 25 on the bottom of the fraction. Denominators cancel, and so 7/24 would be the value for tan beta in this example using both the quotient and reciprocal trig identities. Granted, these two examples are a little bit trivial given that we've worked with these identities for a while, but there are new identities to start to work with. They're called Pythagorean identities. And there are 3 of them. This one you must know, you must memorize as soon as possible, and you must always recognize it when you see it. All right. The other 2 you should see and think about, but they're not as important that you memorize them immediately. But the sine squared plus cos squared equals 1, uber important. Tangent squared theta plus 1 equals secant squared. And then the third one is cotan theta plus 1 equals cosecant squared of theta. So all are important, all are used often in trigonometry and in calculus, but the first one, just uber important. I'm going to take a second to prove the first one, or actually to derive the first one from information that we already know. So if I look at the unit circle and I choose a point on the unit circle anywhere, let's say I choose this point, then the triangle that relates theta, or that ties the side lengths together, has a coordinate on the unit circle of the x value and the y value, so xy coordinate. But we know that on the unit circle, when the radius equals 1, that sine theta is our y value and cosine theta is our x value. So I can say cos theta and sine theta is the coordinate for this point. So I'm going to pull this triangle out so I can look at it more clearly. First, I know it's a right triangle, which means the Pythagorean relationship applies. I'm talking about the angle theta, and if I know that the hypotenuse equals 1, then a squared times b squared equals 1 squared. Nothing new there, but we also know that a, which is our x value or x ordinate, can be written as cos theta. So that means a squared is the same thing as cos squared of theta, and b squared is our sine squared of theta. So the Pythagorean theorem says that cos squared theta plus sine squared theta equals 1. And that's exactly what our Pythagorean identity tells us. And manipulating cosine and sine using reciprocal and quotient identities leads us to the second and third Pythagorean identities. I think this is a good time for an example. Given that sine x equals 1/6 and the cosine of x is greater than 0, so I know that whatever x is, it's in the first or fourth quadrant, and that it has a sine value of 1/6, we want to find cotangent and secant. Well, I could try using a reciprocal and the quotient identities, but don't write this down, I'm going to erase it. But the cotan of x is equal to cosine of x over sine of x. Cosine I don't know, but I know that sine x is 1/6, which means that the cotangent of x is 6 times the cos of x. Problem is I don't know what the cosine of x, except that it's positive. I don't know the cosine of x, so I'm stuck. But I can use the Pythagorean identity involving sine squared. So I have a sine squared Pythagorean identity and plus sine squared plus cos squared equals 1. Let's look for cos squared by plugging sine squared into the formula. So I'm going to solve the formula for cos squared of x equals 1 minus sine squared of x. Now I can just plug in my sine squared, 1 minus 1/6 squared, which is 1 minus 1 over 36, which is 36 take away 1, 35/36. So now I know what cos squared equals, so I can say that the cos of x equals the plus or minus, which is actually not necessary because I know that the cosine is greater than 0, the square root of 35/36, which means the square root of 35 over 6. So my cos value is 35, or root 35 over 6. Now finding cotangent is super easy. If only I were to write the right identity, it would be easy. So cos x root 35 over 6 and sine x 1/6. Denominators cancel, and so the cotangent of x equals root 35. And having that value makes it super easy to find secant. Secant of x is 1 over cos of x. And we found cos of x right here. So that's 1 over root 35 divided by 6, which means 6 over root 35, and rationalize the denominator, 6 root 35 over 35. And so now I have found cotangent and secant using the Pythagorean identity. But suppose when I got to this stage, I wanted to have a greater level of confidence that I had the right answer. I had cosine of x, but is this correct? Because I'm going to use root 35 over 6 to do a lot more work in this problem. Well, that's easy enough, right? All we have to do is use whoops, that's not the one I wanted. The cosine. If I were to check using cosine and sine in the Pythagorean identity, I could discover whether or not I had the right answer here. Once I was right here, I can feel pretty confident as I go farther. Well, let's check our work. We know that the sine squared of x plus the cosine squared of x equals 1. So if I put in the sine squared, 1 over 6 squared plus the cosine squared, root 35 over 6 squared, does that equal 1? I don't know. Let's see. 1 over 36 plus 35 over 36 equal 1. Well, 35 plus 1 is 36 over 36 equals 1. Done. That's correct. So I know my work at this stage is correct. I could do the same thing, I think. Let me look. I have a secant value, which means I would need a tan value somewhere in my givens. That's the only one I can really check. Once I know that cosine and sine are right, then cotan could be double checked, or that's just a direct identity. So I trust this one. And then once I have a cotan, I could check secant with a tan. I could take the inverse of this. So we could do that just for an example. If I use tan squared, let's keep our variables consistent. If I use tan squared of x plus 1 equals secant squared, right? So I can use cotan, which is the inverse of tan, right? I can use this cotan, and I can say 1 over root 35 squared plus 1 equals secant squared. Well, here's my secant. 6 root 35 over 35 squared. Now, all I have to do is keep working to simplify. I get 1 over 35 plus 1 equals, and I'm not sure if this is equal, so I'm going to put a question mark, equals 36 times 35 over 35 squared. 135 cancels, and so I get 35, find a common denominator, 36 over 35 is equal to 36 over 35, and obviously I have the right answer all the way down my work. So, trig identities, we already know some of them. 3 more super important, 1 super duper uber important, the sine squared plus cos squared equals 1. They can be used to find alternate trig values and also can be used very efficiently to check our work because it's really difficult in trig functions to check otherwise.